Thank you. Thank you very much for the nice introduction. I'm very happy to be talking here. And just so you know, I will be sipping some coffee. So if you see that I'm a little bit sleepy, it's that it's a little bit early here. So please just ask as many questions as you want. And I just so you know, I'm actually looking at the chat, so I will be able to answer the questions as we are going. So what I want to talk today is a recent work that I did with a fantastic group of other researchers. But the way that I want to present it is as you're seeing on the slide. So I'm going to do a very brief introduction of what is representation theory, just because I wasn't sure if everyone was on the same page. Or even like if you are in the same page, if you know what is representation theory, I kind of like want to tell you in 3 slides, how do I understand it, or what is my way of thinking about representation theory. Then I want to recall you or present to you what is the classical RSK algorithm. And then I want to start like switching a little bit. So the first thing we are going to do next is rediscover it. So I'm going to switch a little bit the algorithm. And then I want to apply it to what are called partition algebras or diagram algebras. So I'm going to introduce those algebras. I'm going to tell you how we apply the RSK algorithm in this case. And then we are going to just end with some consequences in the representation theory framework. So the way that I usually think about representation theory is that we are trying to understand abstract algebraic structures as we understand vector spaces. So the way that we are going to be doing is that every element in my abstract algebraic structure is going to be represented using linear transformation of vector spaces. And in my mind, this linear transformation of vector spaces, there is going to be matrices. Because I'm going to be restricting to finite structures or structures that behave well with the vector spaces. So let me show you how we do that. The way we are going to be doing that is we are going to fix a vector space over a field. In my mind, or for the kind of like presentation I'm giving today, it's enough to just consider C to the n. Then I'm going to consider the general linear group of V. This is the group of linear transformations that go from V to V. Because in this case, I'm taking V to V, C to the n, I'm just looking at matrices, vertical matrices. So this is the group of GLN with complex numbers. Now I need to kind of like fix my abstract algebraic structure. So I'm going to either have a group of an algebra. For the sake of this example, I'm going to choose the group. And then when I talk about a representation, what I'm talking about is this vector space, V, together with a map rho. This map is going to be a map that goes from the group of the algebraic structure to GLV, and is assigning to every element G an element in this group, which is basically another map, another function that goes from the vector space to the vector space, and I'm just assigning to every element another element. So what I'm doing here is that I can encode this map. If I'm taking in the case of taking C to the n, I can encode this map with a matrix. And for what many people talk about when they say, I'm talking about an action, they are actually having a representation, because many people denote this as an action. So what they are doing here is that usually what happens is that we do not record the row. We will just have V as our representation, and we are going to describe what is the action. So you can either do the two things, but those are equivalent definitions. It's just that depending on with whom you're talking about a representation, they will give you one perspective of another. Now, I was telling you that I want to do representation theory as I do linear algebra. So I need kind of like some components from linear algebra that we can translate into representation. So we have what is a subrepresentation. It's just I'm taking a linear subspace such that is stable under the action of the group. And what we need to do is we just need to restrict our map. And the fact that it's stable under the action means that I'm not being outside my subspace when I multiply, when I act with an element. Now, among all the representations, there is going to be a set of them that are going to be our basic elements, and those are the irreducible representations, and I will refer to them on the slides a lot as irreps. And those are exactly those representations that only have two sub-representations, the trivial subspace and the representation itself. So this is kind of like the subspaces that were in, the subspaces that are the ones that we want to consider in this case. And now the third element that I'm gonna need in this case to kind of like illustrate a little bit what we are doing here is that I can construct new representations from all ones. So we have several operations with representations. So I present here three. We can consider tensor product, which is also known as the Kronecker product. We can restrict or induce, which is basically moving when I have a group or I have an algebra, I can have a subgroup or a subalgebra. And then I can be looking at what is the relation between the representations in the group and the representations in the subgroup, going in one direction or the other. And the third one that is a little bit more complicated is that I can actually compose representations in some special cases, and this is also known as the Plethesian problem. Now, the problems that I care about are related to the EREPs. So what I want to do is I want to do three things. I want to characterize the set of EREPs. That is, I want you to give me a set that is indexing all the irreducible representations. I want to be able to compute the dimension of those EREPs because that is going to help me also when I try to decompose into irreducibles. So if you have an operation, you want to decompose into irreducibles, and then you want to see how are like those coefficients and things like that. So knowing the dimensions can be very helpful. And that is where kind of like the combinatorics plays a role. So I'm going to show you an example in a very small table what I'm talking about. So if I'm taking the symmetric group, which is the group of permutations, then if I'm looking at the set of EREPs, from the algebraic perspective, I'm just having as lambda, where from the combinatorial perspective, this lambda over here is actually a partition. So what we are doing when we are looking at the set of irreducibles is that we are encoding the cycle notation of the permutations. Now, if I look at the dimension, then what happens in this case is that from the combinatorics point of view, this is the number of standard tableaus, which is an object that I'm going to define in a couple of slides. And when I talk about the composition, is that I can take two irreducibles representations, I can consider the tensor product of them. And now what I want to do is I want to decompose into EREPs. So I'm going to have that each of the EREPs appearing is going to have a coefficient. That is how many times it's repeated. And those coefficients over here are what are called the Kronecker coefficients. So can we find, this is supposed to be a tensor. Can we define or can we describe these coefficients with a combinatorial rule? And for the Kronecker coefficients, there are many results out there, depending on the shape of your lambda, mu, and nu. So this is kind of like the representation theory in 3 slides. But let me now tell you what are the insertion algorithms or the RSK algorithm. So the idea here is that we are going to have a bijection between a set of sequences with some properties, and then we are going to have pairs of tableaus, which I'm going to define in the next slide. The consequences are that they help us to understand better the representation theory, and I hope I can convince you of that during the talk. Now, the classical RSK, this RSK is coming from Robinson, Stenson, and Knuth. It's going to be our starting point of reference, and that's why I want to like give you the classical version of it. And then what we have been doing is we have been exploring some variants that are going to be helpful for diagram algebras, and that also will behave with when we restrict to subalgebras. So I will also describe what are the diagram algebras and how we restrict it. And just as a motivation, just letting you know that it's coming from the 2 problems that I talked about before, the Plethesian and the restriction problem. But I'm not going to talk in detail on how these things are connected. Now, just to make sure that everyone is on the same page, when I talk about a partition, what I'm having is a sequences of weakly decreasing numbers. They all, when I say it's a partition of L, that means that all of them sum up to n. And they are all positive integers and are not 0. And if I'm thinking about a partition, what I'm actually thinking is about a diagram. So what I'm having here is that this partition over here has 4 boxes, 2 boxes, 1 box, and 1 box. And these numbers here are just telling me the number of boxes in each row. And I'm using what is called Fresnel notation because I'm putting the diagram on the left south corner. And what we are going to be doing during the talk is we are going to be considering fillings of these diagrams. Those are called John tableaus. And the fillings that we are going to consider is going to be either with numbers of set of numbers that I'm going to also call multisets. We are going to do it in a standard or semi-standard way, which basically a standard means that I'm going to have all the numbers, all the consecutive numbers, 1 up to something. In this case, you see that I have 1 up to n. And if it's semi-standard, then I'm going to allow to have repetitions, and I'm going to be allowed to miss some numbers. And then the conditions that I'm going to stipulate for my columns and rows is that they need to be, like, I can only have repetitions on the rows, and they need to be increasing in these 2 directions. So in this case, because I don't have repeated numbers, there are no repetitions on the rows, but the idea is that these are weekly increasing. And yeah. Okay, so let me kind of like give you where the RSK is coming from. So I'm going to have some initial input, and then I have pairs of tableaus. So in each of the cases, what I'm going to be doing is I'm going to be switching the initial input, and that is going to have consequence of the pairs of tableaus. So what Robinson did, he took the permutations in SN, and he constructed a bijection with pairs of standard John tableaus. So here what I'm going to have is all the numbers 1 up to n in each of these. And they're going to be covering all the possible shapes, all the possible partitions of n. Chen then said, well, there is nothing special about permutations. I can actually extend it into words. So what I'm going to have now is I'm going to have like sequences of numbers that are in the set 1 up to n. So this is denoting my alphabet. So I have all the numbers 1 up to n. And what is going to change now is that I'm going to still have a standard John tableaus on the right, but on the left, now I'm going to be allowed to have repetitions. So I'm going to have semi-standard John tableaus. And finally, Knuth, a few years later, said, well, we can actually completely generalize that by considering generalized permutations. And I'm going to define those later when we do the example. But what I'm going to get in this case is semi-standard John tableaus on both sides. So let me give you what are like kind of like the ideas behind the RSK algorithm. So what I need to have is I need to have 2 order sets. For the case, the general case, that is a generalized permutation, we are going to take these 2 order sets to be the set 1 up to k and 1 up to n. And then I'm going to write my generalized permutation as a 2-line array. So I have a row with numbers in A and a row with numbers in B. And what I'm going to be doing is I'm going to be ordering them in such a way that the top row is fully ordered. So I have all the numbers in weekly increasing order. And then when 2 numbers are the same, then I'm going to order by the second row. So let me give you an example of generalized permutations. I also want to mention that both words and permutation are particular cases of this. So if I have a permutation, if I write it with 2-line notation, as I have here, I have the numbers 1 up to 5 on top, and then I describe my permutation below. So in this case, what happened is that both rows are going to have all the numbers 1 up to 5. Now, if I look at a word, then what happens is that I have my word. We usually denote it like this. So what I'm doing is I'm putting a row on top of it with the numbers 1 up to 5 in this case. So you see the difference between permutations and words is that the top row is the same, but now the bottom row here, I have all the numbers, and here I'm allowing to have repetitions. And what I'm saying is that you see that I have 3, 4, 5 here, and all of them has 2. Now we go to generalized permutations. And what happens here, you see that I have the top row is in increasing order, even with repetition. And every time I have to repeat in entries, then I'm ordering by the bottom. And this is a generalized permutation. So what I want to do is I want to show you step by step, or a little bit, at least a few first steps how I can describe this map. So what I'm going to be doing is I'm going to take a generalized permutation, this one over here. And what I want to obtain is I want to obtain 2 standard Young tableaus. And in this case, I'm going to obtain these 2. So let's see how we do that. The idea is that I'm going to row insert the bottom row, and then I'm going to record the top one. So when I was thinking about having 2 tableaus, I usually think about this as the insertion tableau, and this one as the recording tableau. So let's start doing it. So when I start with the first pair, the 1, 1, there is nothing to do because I'm starting from empty. So I insert and I record. That's all I have. So I'm gonna be color coding. The bottom row is gonna be my insert tableau, my insertion tableau. So it's gonna be in blue, and the red one is what I'm recording. So it's gonna be in red. Just don't get confused. The bottom row goes to the left. The top row goes to the right. And in the ones that are coming, I'm gonna be keeping what I had before next to it in a race, in a shade, in a saddle. So we look at it. Now, when I try to insert the 5, if I can put it in the first row and I'm not violating my conditions on having increasing rows, then I just do that. So I insert the 5. If I compare this tableau with this tableau, this is the new box, and this is what I record, the other one. I'm gonna do another 1, 5. So I insert another 5. Remember that we are allowed to have repetitions on the columns, on the rows. So this is perfect. And now if I compare this one and this one, this is my new box. So I record this one over here. Now let's get to we get to a conflict now, because now I want to insert these 2. But if I look here, if I put the 2 here, this will be a problem because I have a 5, 2. So what I'm gonna do is I'm gonna put the 2 here, and this is kind of like bumping the 5. So the 5 now is gonna be here outside, and now I have to insert. But because I know I cannot, like I already insert something in the first row, now it's gonna go to the second row. Because the second row is empty, I'm just gonna put it here. So what this has done is I have put the 2 in the first row, whatever it should be, and I'm bumping the box that is there. Now, if I look at this diagram and this diagram, the new box is this one. So even if I put the 2 here, the new box is here. So I record this 2 in that box. And I'm just gonna keep doing that. So now suppose that I insert a 3. So if I look at this tableau, the 3 should go where the 5 is. So I just put the 3. And now the 5 is in the second row. Because I have no problem with weekly increasing rows, I can just put it next to it. And if I look at this tableau and this tableau, this is the new box, so I recorded 2. Now, I want to show you one more step on how we get 3 rows. So if I look at this one, if I have to insert here, the 1 should go in the place of the 2. Which means now, so I have the 1 here and the 2 goes out. Now, if I insert the 2 in the second row, it should go on the spot of the 5. And now the 5 is the one that is on top. And now I'm avoiding rows 1 and 2 because I already insert something there. So I should put it here. And that's how I get this tableau. And if I compare my original one, the small one here, with this one, this is the new box. So I record the 3. There is a question. Yes, John. I don't know if you're writing on the chat or you can also mute yourself. Okay, there is no question.
Yes, John, you need to unmute, maybe, yeah.
Okay.
Everybody is unmuted, so they can unmute themselves when they want. So maybe John, you want to ask something? No, I think it was a mistake.
Okay. So if you continue doing that, we stop at this point. If we continue inserting this row, we will get to these 2 tableaus. Now, why do we care about this? Well, we do care. I mean, I think it's a beautiful result, but we do care also because it helps us a lot with representation theory. So let me kind of like show you how the representation theory shows up for the extended version of the RSK. So in representation theory, there is something called the Schur-Weil duality, which is basically the following phenomena. I'm going to take as my vector space C to the n, and now I'm going to compute a tensor of B with itself k times. So if I look at this, I have two actions. I can act on the left with matrices, with GLN, which is basically going to just like switch tensor, apply the matrix to each of the elements in the tensor product, or I can also act on the right with SK, which is going to permute elements in the tensors. Now, these two actions are actually what are called commuting actions. I can do one or the other in different orders, and I will get the same. And that creates the following phenomena. That means that I can decompose this V tensor K as a direct sum where I'm having a smaller tensor product of smaller spaces. So what I'm having here is I'm going to have a subspace with a GLN action and a subspace with an SK action. So what I'm trying to do here is I'm trying to look at a space that is complicated, and I'm decomposing it into smaller pieces that I know how to understand, because these are going to be E-reps for GLN and SN. So this is a kind of like a very, yeah, it's a very common kind of like duality when it comes to representation theory for finite groups or for some type of groups. And what happened is that RSK kind of like illustrates this decomposition. And is that it do it with an enumerative result first. So what I'm going to do now is if I look at the Schur-Weil duality, I have this equation, I can count dimensions. So if I'm looking at, because I have C to the n tensor K, I have n to the K as the dimension of this space. And now I can tell you that if I look at I told you in the table that the dimension of the symmetric group were the number of standard germ tableaus. And what happened with the GLN E-reps is that the dimension is the semi-standard germ tableaus. And now is when the RSK algorithm comes in. Because now what I have is that this bijection is actually, this enumerative result is actually resembling this bijection. I'm having, on this side, I have words of length K in N. And on this other side, I have my pairs of tableaus that I had before. So this is actually extension result. Now we went in this direction. I have the Schur-Weil duality, I'm counting dimensions, and I'm doing RSK. Could it be also possible that we can go the other way around? Because I have an RSK algorithm, then I'm going to have an enumerative result. It's an enumerative result saying anything in representation theory world. So that's kind of like the idea of how the RSK algorithm is helping us in the representation theory, that I can go in this direction, but I can also go on the opposite one. And that is kind of like what happened in our case. So what I want to do now is kind of like I want to switch a little bit, and I want to explain you what we're thinking about instead of inserting numbers, inserting sets of numbers. So I'm going to go back to the generalized permutation that we had, and I want to twist it a little bit. So instead of looking at it as this two-line array, I'm going to do the following. I'm going to look at the numbers 1 up to n at the bottom, 1 up to 5 in this case, and I'm going to record on top what are the entries that I have. So if I look at the 1, I have a 1 here, a 1 here, and 2 1s here. And if I look at the numbers on top, I have 1, 3, 4, 6. So I keep them as a multiset. And to have multiset, we are just going to put these two brackets. I do the same with the 2. So with the 2, I'm going to have this 2 and this 6. With the 3, I have 2, 3, and 6. Now 4 doesn't appear, which means that then I just have the empty set, which is a normal set. And finally, I have the 5. So I have 1, 1, 3, 3, 1, 1, and 3, 3. And that's it. So I have this new encoding. Now, remember when I was doing RSK, I had something that said, and now we have to kind of like order according to the top row. And in this case, that's what we are going to be doing. We reorder, and we are going to be reordering using the graded lexicographic order, which is basically like the sets I'm going to order by size. And once they have the same size, I'm going to order as like using the alphabet. So for instance, these first three, because I have 0 elements, 2 and 3, they are just in increasing order. But if I look at these two, both of them has 4 elements, but this is 1, 1, and this is 1, 3. So this is smaller than this one. And then I just like, when I move them, I just keep track of the bottom row. And now this is a 2-line array that I can insert as I did before. I insert the bottom row. And now when I'm recording, instead of putting one number, I'm going to put more than one, but that's totally okay. Okay. This is not ordered. This is recorded. And when I do that, what happens is that I get these other pairs of tableaus. Okay, so on this side, I have just the numbers 1 up to 5. And here I have all the multi-set. And now just like see that I have like deleted all the commas. This is 2, 6. The empty set is just an empty box. And because like you think about it, the empty set is going to be the first one. It's always going to be here. And there is nothing smaller than it. So what we were doing here is we were having this, we have this bijection that goes from generalized permutations. And now on the right, I have standard Young tableaus, and on the left, I have standard Young tableaus, and on the right, I have a standard multiset. So this is the result that we figure out with this bijection, and this is the classical result. So you see here that we have switched the roles of the standard Young tableaus, and that by switching the roles, what happens is instead of considering semi-standard, we are considering a standard multiset. And now a very fair question will be, are there any algebraic structures in representation theory that are going to reflect these results? And I can tell you that yes, there are. And these are going to be the symmetric group and the partition algebra. And that is where the diagram algebras and the partition algebras appear. Now here, I have kind of like the same result that I have for the surduality. I need some conditions saying that n is larger or equal than 2k, and that's because of being simple. The partition algebra is semi-simple only in general, only in this case. For n smaller than 2k, you actually have to do case by case. But when n is large enough, which is gonna show up eventually when I show you the diagrams we're gonna have. But what happens here is that I'm gonna have the symmetric irreducibles on one side, the symmetric group irreducibles, and on the other side, I have the irreducibles for the partition algebra, which I haven't defined yet, and I know it. But I kind of like want to show you something else. What this is saying is that the dimension of the partition algebra is actually, the irreducibles of the partition algebra is actually the number of standard multiset tableaus. So that was kind of like one thing. And now I wanted like to twist it a little bit so I can show you a variation, and I'm going to show you the motivation on why we were looking for this other variation. So one of the things that happens with the order that we chose for the 2-line array, this graded lexicographic order, it was that it's a good order, but it wasn't giving anything else. So we thought if there was something else we could do that will help us in this case. So let me show you what we were trying to do. So we look at a Stenset result. We are going to look now at what was Robinson result. Robinson did permutation, so I have n factorial as a numerative result. And on the other side, I had tuples of standard Young tableaus, which means that I have this sum of squares of the same thing. But we also have that, we also have all these things over here. So we also have that we have, like, we want to look for a reasonable result than this one for the partition algebra. So let me go to the next slide because it's better. So we wanted to figure out if there is a way of saying the dimension of PKN, which is the partition algebra, is actually the sum over squares of the same thing. Can we design an RSK algorithm that is going to solve this other identity? So the identity that we had before was the dimension, what was multiplying. It's not. It's multiplying. So we like, the idea is that we were looking for this other, an algorithm that is designed, that is talking about this. And the solution is yes. That's what I want to talk about. So let me show you this other variation, and I'm also going to talk about how it restricts to other subalgebras. So what I mean by other subalgebras is this thing over here, this table. So this table, what it does is has the partition algebra on top, and it has another, like, a bunch of subalgebras that are subalgebras of the partition algebra. The dimensions of the algebras and the dimension of the EREFs are known for all of them, are the ones that are in the table, and these are all the references. So what we were able to do was to find an RSK algorithm that give us these formulas by just using the same algorithm, and instead of having different ones. So all these references are mostly different models for each of them. So what we did is kind of like put all of them under the same umbrella using the same model. So let me tell you what are partition algebras or diagram algebras. And you're going to see in a minute why I'm using both names. So the idea of a partition algebra is that I'm going to take two alphabets. So I'm taking the numbers 1 up to K. And I'm taking the numbers 1 bar up to K bar. So what I'm doing basically is I'm keeping two copies of the numbers 1 up to K, but I want to differentiate them. So instead of using two colors, I'm using non-bars and bars element numbers. And what I'm doing is I'm going to look at all those numbers and I'm going to consider a set partition. So you have an example here. I'm taking the numbers 1 up to 8. And you see that I'm putting, I'm just 1 up to 8 and 1 bar up to 8 bar. And I'm just putting them in groups, in sets. So that's a set partition. So as a vector space, the partition algebra is just the span of these set partitions, what I have over here. Now, there is a way of constructing an algebra from a span, but it's not going to be very relevant for us. I'm just going to comment how I compute the product in a minute. So instead of looking at the set partition just by like the sets, what I'm going to be doing is I'm going to look at them with diagrams. So what I do is I'm going to put the numbers 1 up to 8 on top, the numbers with the bars at the bottom, and everything that is in the same set in my set partition, I'm just going to link it. And I don't care how I linked it, as long as all the numbers are attached to one of the numbers in the set. So what we did for standardizing that is just that I'm just going to do kind of like link them in order on top, link them in order on bottom, and then just close it. So you see here I have 1, 2, 4, 1, 2, 4, have 2 bar and 5 bar, and then I just kind of like close it here. So I will get this element. The 3 is by itself, so I don't do anything. The same with the 1 bar here. The 8 and the 8 bar, they are just linked together. And then this other one, I have 5, 6, and 7, 3, 4, 6, and 7, and I just close it. Now, if I want to multiply two diagrams, I will put one diagram on top of the other. I will just follow all the path, and then there will be a coefficient depending on what are the things that kept on the middle. And that's where the dependency on n arises. But for the sake of this talk, we don't actually need to talk about the structure of PKN as an algebra. We don't need to define the product. So I'm just going to skip it, if that's okay. Now, I want to do an RSK here, so I cannot have to translate this set partition of this diagram into something that resembles to a two-line array. So I'm going to do it the following way. I'm going to look at what are like propagating blocks and non-propagating blocks. So propagating blocks are blocks that have vertices from both sets, vertices with bars and non-bars. So this will be a propagating block. This is a propagating block, and this is a propagating block. And then the other ones are non-propagating. So I have 3 and 1 bar. So the propagating blocks are the ones that are going to give us the two-line array that we need. So we are going to do that just by putting, this is like a kind of like a complicated slide, but I will do an example in a minute. So what I'm going to do is I'm going to do the propagating blocks. I'm going to put the numbers with bars at the bottom, the numbers with non-bars at the top. And those are going to be like small sets. And I'm just going to order them. And the order that I'm going to use in this case, and this is kind of like important, is the last letter order. So when I'm comparing two sets, I'm looking at the largest letter. And I'm just ordering by that. And then I'm just keeping on my side the non-propagating blocks, and that will give me another step in my RSK. What I'm going to do, so I have my set partition, I have propagating blocks and the non-propagating blocks. The propagating blocks, I put them as a two-line array. I'm going to apply the RSK, the regular RSK algorithm to that. And I'm going to get two tableaus, PK, P and Q. And now what I'm going to do is I'm going to add a row of empty cells followed by the non-propagating blocks. So let me give you an example because it's more visual than using the slides description. I took a little bit different set permutation than the one that I had at the beginning. I wanted something larger. So I look at the propagating blocks. I have 2, 3, 4, and 4 bar, 5 bar. So that is giving me this column here. I have the 2, 3, 4 on top and the 4, 5 at the bottom. If I look at the 1, 6, 7, 8, I have this other one, and so on. So these are actually these 3 and this one are all the propagating blocks. And I just put them in order. So if you look at them, 4 is smaller than 5, is smaller than 6, is smaller than 9. So that's what I meant with the last letter order. I just look at the largest letter and I order by it. And then I can apply the regular RSK. So when I do, I get these two tableaus. And now what I'm going to do is I'm going to add a whole row of empty cells, and then I'm going to add the non-propagating blocks. In this case, the non-propagating blocks were this one and these two. Well, actually, let me do it that way. So I have the 1 bar and 9 bar here and the 7, 8. And what happens here is that the total number of boxes equals n. So you remember that I have my PKN. So the K is gonna tell me is gonna be the size of the alphabet. And now because Kn is larger or equal than 2K, which is what we are considering in the stock, I have that this is always is not gonna give me any problem with this. So that's kind of like a very strange initial condition or way of constructing, but it's actually very consistent with the idea of the partition algebra. Okay, so let me just give you as a corollary numerative result. So what we did was proving that this is a rejection. So I have set partitions of these two alphabets, which as a numerative result, they are counted by the bell numbers, B2K. The 2K is just because I have 2K numbers in total. And this is telling me that this is actually the sum of all the number of the standard multisets squared. And that is exactly the result that I was looking for, the partition algebra, because this is the dimension of the partition algebra and this is the dimension of the irreps. So what we did was writing that the dimension of the PKN equals the sum of the dimension of the irreps square. So this is the version on representation theory of this enumerative result, which is coming from our projection. And then if you know a little bit more about RSK, that is a very nice property. If you switch the order of the rows, like you flip them, that usually corresponds to flipping the P and the Q, the two tableaus, and that also happens in this case. But that was more like a note on the side. Okay. So one natural question is, does this algorithm work when we restrict to subalgebras? And you will be thinking that I haven't told you what are the subalgebras. So just bear with me one more slide. So I was telling you that the partition algebra, I was also calling it a diagram algebra. And we have this diagram, so we can actually put like restrictions coming from graph theory. That's the way I usually think about it. So we have what is a planar graph and things like this. So we can kind of like translate those properties, being planar, a perfect matching, or just a matching, or like a permutation or a partial permutation. All of these are conditions that are coming from kind of like graph theory, but I can impose in these diagrams. So because I'm looking at the span, because I'm defining the partition algebra with as a vector space as the span of these diagrams, I can also do it with the subalgebras, and then they will be automatically algebras. So that will be no problem. And what happens is that each of these restrictions corresponds to one of the, I don't know if I don't have a table next, corresponds to one of the subalgebras that I told you on the table. So let me kind of like summarize what we did. Now, instead of having set partitions in general, I'm going to have set partitions with some properties. These are coming like these properties are the ones coming from the graphs, from the diagrams. And then those are going to be in one-to-one correspondence with pairs of tableaus. So what we did was characterizing the set of the tableaus that appears for each of the set partitions with properties. And then we proved that we still had bijections, which was basically restricting our algorithm to this set partition with properties. And we also did some connection with other models, like the vacillating tableaus. But the main advantage here that it was that we have one algorithm to rule them all. So we only needed one algorithm to prove this kind of like result. So let me show you again the algebra. So each of these algebras, so if you think about the group algebra, that's the one corresponding to permutation. So then you are saying, okay, then I have permutation. If I want something that is planar, then that is going to be, I think it's the temporally leaf algebras. So those are where the diagrams are, how do you call it, planar. And yeah, I have one more slide with what are the consequences. So this table summarizes the dimensions and the dimensions of the irreps. And what is going to happen is that for each of these subalgebras, we are going to have the same result that we had for the partition algebra. So what I have is that if I write as a K, one of the algebras of the subalgebras in the table, what we are showing with our RSK algorithm is that the dimension of those algebras is actually the sum of the number of standard multisets squared. We are also showing that actually the dimension of like this number is actually the dimension of the irreps. And to do this, we actually had to understand what are like the Bratelli diagram on how to stack, how to put one algebra inside the next one when I'm increasing K. And we also have to give an explicit description of the branching rule. So if you know a little bit more about how is the RSK and how you prove the dimension of an irrep, that is in this case a very combinatorial one. And one could think then that we could go back to our duality result and say, well, you have this duality for the partition algebra. Can you have such a duality for the other algebras in the table? And I have three here. I have that for the symmetric group, yes. I just need to put the GLN on the other side. For the partition algebra was true because I just have the symmetric group. There was another algebra that was the Brauer algebra, for which we can also do it in the orthogonal group. For the other ones, it's becoming more complicated and it's not clear that you can always have it. So that's what we are trying to work out at these days. So that's kind of like the continuation of the project.